Hello, my name is Cooper Selco, and I'm a first-year PhD student in Applied Science and Technology at UC Berkeley. I work with Professor Ashoka Joy in the field of nuclear magnetic resonance. I'm focused on pushing the boundaries of nuclear magnetic resonance by using new techniques such as optical hyperpolarization, building novel instrumentation, and studying spin physics at the nanoscale. So, according to quantum mechanics, particles have some intrinsic angular momentum called spin, and this causes particles to behave like tiny bar magnets. So, just like how a compass needle aligns with the Earth's magnetic field, spins in an external magnetic field will align with it in order to minimize magnetic energy. However, unlike a compass needle, spins in a magnetic field will move around the field, and this kind of motion is called precession and is shown in the figure here. So my research is in nuclear magnetic resonance, or NMR, and there's three basic steps to doing an NMR experiment. Step one is to align the spins with an external magnetic field. Step two is to send a current through a wire loop that's next to the sample, which will generate a secondary magnetic field, which will rotate all of the spins. And then in step three, we turn this current through the wire loop off, and we allow the spins to precess around the original magnetic field. And these precessing spins will create a changing magnetic field, which will induce some current in the wire loop, which we detect as the signal in our experiment. And so the frequency that these spins precess at, and therefore the frequency of the current which we detect in the coil, depends on things like what kind of nuclei you're observing and also the local electronic and magnetic environment of the spins. And so this allows you to do some very powerful things like determine molecular structure of chemicals, and also it's the basis of how MRI imaging works. So to get more specific about my research, I'm pushing the boundaries of NMR in a number of ways. One way is through optical hyperpolarization. So in this technique, we shine a laser on the sample, which will polarize electrons, and then we can transfer polarization from the electrons to nearby nuclei, and this will make the signal of our NMR experiment much stronger. And so it can enhance the signal by about 1,000 times. I'm also working on some novel instrumentation, which will allow us to explore NMR in new regimes. So in the figure here, I've helped build an apparatus that can go to low temperatures and also variable magnetic fields during an NMR experiment. And so in this instrument, we put the sample inside of a cryostat at extremely low temperatures, and then the cryostat is attached to a motor, which can push and pull the cryostat into and out of the magnet during experiments. And then finally, I'm interested in studying nanoscale spin dynamics in hopes that this will allow us to do some interesting quantum sensing and nanoscale MRI imaging.